Hey everyone, this is Dr. Walker. In this video, I'd like to go over the third example from v585 on motional EMF. This one is called motional EMF induced in a rotating bar. Up to now, we've been dealing with straight bars, straight conductors, moving in a straight line, right? In this case, we have a straight conductor, but it's rotating about a point right here, and it's rotating with a constant angular speed omega. And it does have a length L, just like our conductors usually have a length L. There is a uniform magnetic field directed perpendicular going into the page. We're looking for the EMF induced between the ends of the bar. So you may think, well, how in the world do we deal with something that is rotating like this? Well, what we do is we just consider a very small segment. It has already been drawn here. Just consider this to be a very, very small segment that has a length, a dr, all right? And that little segment is moving in a straight line. And so there is going to be an EMF induced in this little segment. And then we can find the EMF induced for that segment and integrate along the whole length of the bar. The reason that we can do that is because we know that if we use Lenz's law, we know that we have, or let's use the right-hand rule number 1, we know that put our fingers in the direction of V to the left and upward, we fold into the page. We know that there's a force downward on the positive charges. So we know all the positive charges accumulate on this bottom part here, and then all the negative charges accumulate on this part. So if we were to do that for another little segment, it would be the same thing, all the pluses on this side, all the minuses on this one. And so these are all just a little bunches of EMFs that we can just add up over the whole bar. They add up because they're in series. They always have the minus on top and a positive at the bottom. Okay, so that being said, how do we find the EMF induced by just one of these bars? We know our motional EMF equation is E equals BLV. Well, and we can still use this, but this time, since it's just a very small element of length dr instead of L, we can just say BV and then dr for the L, and we can say that that's going to induce an EMF DE. That way we can integrate over the whole length of the bar. So the EMF is going to be the integral of BVDR. Now, which of these variables depends on R? B does not, so we can take it out. But V does depend on R. If you remember from Physics 1, when you have a rotating object, all parts of the object have a different V, right? The closer that you are to the pivot point, right, the smaller the R, the smaller the V. If you have a big R, you have a bigger V. And hopefully you remember from Physics 1, V equals R omega, right? That's the equation that tells us if you have a constant angular speed omega, then the bigger the radius, the bigger the linear speed. All right, so what we can do is we can rewrite V as R omega dr. Omega is constant in this problem, so now we can go ahead and take omega out. And we have the integral of R dr. We're integrating over the length of the rod from 0 to L. So we have B omega, we're going to have R squared over 2 that we're going to integrate from 0 to L. And that's going to give us B omega L squared over 2. So I just thought this was a fun problem where you still have an EMF induced in a bar if it's rotating, because it definitely still has some motion in an external magnetic field.